know it's early, at least for me, because I'm 9 hours, have 9 hours of jet lag, but I hope to not bore you to death with this talk and give you some context, like why I came to care so much about this project, and maybe some ways that you might think about getting involved in infrastructure technology for data science and data engineering, or ways that you can support and take advantage of this work. So a little over 10 years, I started writing some Python code for myself to wrangle data. I didn't really know much about open source or expect it to turn into a very big project, and so the last years have been really interesting. I spent a lot of my time from 2011 2012 really focused on building the Pandas project, but about 5 years ago I handed over the reins of the project to the rest of the maintainers, people whose names you may or may not have heard of, people like Jeff Reback and Joris van den Bosch, Tom Augsburger, Philip Cloud, folks who've been really building the project out and making the community healthy over the last 5 years. But I got busy with some other projects that are closely related to Pandas, but not exactly Pandas itself. Probably a lot of you have a copy of my, or some of you have a copy of my book, which is almost in its came out 6 years ago. Or 6 years ago in October. So as Pete was mentioning, funding open source projects is difficult, and I think lately there's a general feeling in the air around funding maintenance of large established projects. So in the wake of really major security vulnerabilities and important software, like maybe a lot of you probably heard about Heartbleed, like it was a major bug in OpenSSL. And after people dug in, they're like, well, who maintains OpenSSL? And it turns out that OpenSSL only had one full-time maintainer, and the other maintainers were working part-time and were all kind of stressed out that they could have security bugs, but they just don't have enough funding to support the project. So a lot of people have been working on how can we get corporate sponsorship to maintain really critical software. So if you think about open source software as a public good, in the sense that we have clean water and roads and sewers, like maybe we should take the same approach to essentially individuals, companies, and governments funding development of open source infrastructure. It's not such a crazy idea, but raising money and having money to build brand new projects is even more difficult, because you have to convince people that you can actually build the project and that it will be valuable. And so I've been building something new the last few years, and so earlier this year I created an organization called Ursa Labs to focus on building the Arrow project with the focus on creating shared infrastructure for data science to accelerate data science and data engineering in Python, R, and kind of across the spectrum of tools that data scientists use. So to do this, I partnered with RStudio and Hadley Wickham, because I wanted I guess kind of in the data science world, we're two of the most well-known people in that ecosystem, and I wanted to have the R community bought in and committed to working together to build software that we can all use in both programming languages. But it's certainly not limited to just Python and R, but that's a pretty good place to start. I had been working at 2 Sigma for the last couple of years, so they're a financial institution in New York City. They're continuing to kind of sponsor the project. So RStudio is committed resources, and I expect to be adding some additional logos to this page over the next 6 months. So if your company or any companies that you work with would be interested in sponsoring this work, we'd be happy to hear from you. But our goal with the money that we're raising is to hire people and have them work full-time doing 100% open source development. So not doing consulting, not building products or any of those things which tend to distract from the core open source development, and doing a good job of building high quality production software. So, one problem that I've encountered over the years is the fact that data systems are highly fragmented when you look under the hood at the tools that they use to implement themselves. So things like how is data stored, how is data deserialized, how is data represented in memory, who wrote the algorithms to compute things on that data in memory. And so a lot of systems are black boxes that are very vertically integrated. So Pandas is one such system that's highly vertically integrated where we wrote our own CSV parser, our own way to read data out, read data from HDF5 files, reading data from databases. We have our own kind of query engine. Pandas is kind of its own kind of in-memory database kind of thing. We have our own front end, and the front end, the Python code that you write is tightly coupled to the back end. But it's a complicated thing, and one of the issues is that we don't have a lot of open standards. So open standards help with making things simpler by using common technology that makes systems interoperable and makes things less fragmented. And so for me, the two things I'm most interested in is sharing data without having to copy or serialize, and sharing code, so being able to take an algorithm that somebody else wrote and being able to run it on my data without having to rewrite the algorithm. And those two things historically are very difficult. So we have lots of open standards already. If you're in the big data world, you might be familiar with some of the storage formats like Parquet and Orc that have come out of the Hadoop ecosystem. There's things like HDF5 for storing general numeric data sets. We have general structured data serialization tools for RPC. So Arrow came out of the Hadoop world. We also have protocol buffers and Thrift, which is, I don't know the history, but I think Thrift was created by ex-Googlers who wanted to have an open source version of protocol buffers, and then Google open source protocol buffers. So now we just have lots of incompatible tools. Some people think of CSV as being an open standard, but it's not, because there's no standard way of serial. I guess there are some standards for writing down schemas for CSVs, but the amount of variety and different options in parsing CSVs makes them a poor choice for warehousing data. So given that we have lots of fairly standardized accepted ways of serializing binary data, we don't have a lot of standards for in-memory data. And so if you want to share algorithms that execute against in-memory data, you need to have open standards for in-memory. The main one that we have is the multi-dimensional array model, which came out of basically APL and Fortran. So when when folks built MATLAB and they built NumPy, they already had a memory model for representing multi-dimensional arrays. Like, okay, here's a data pointer, here's shape and strides to instruct the code how to iterate over, interpret a block of memory as being a multi-dimensional array. But when you have a standard memory model, that means that two processes can move data through shared memory without any conversions or copying. You can send data through a socket, receive it on the other side without performing any additional conversions outside of the socket send and receive. If somebody writes an algorithm, you can invoke that algorithm in a different context. So that's how we've been able to reuse decades worth of linear algebra code written in the 70s and 80s. A lot of it's still in Fortran. If you're in the Java world, you can create bindings to C and C++ code and invoke, assuming all the data is in off-heap memory, you can invoke algorithms that are written in C and C++ on data that was generated by the JVM. So you get lots of good benefits when you standardize in memory. But when you go beyond multi-dimensional arrays to tables and data frames, essentially, so if you're a data scientist, probably use data frames. I guess everything has data frames now. Spark has data frames, Pandas has data frames, R has data frames, Julia. Every language has a data frame, but when you look under the hood of what's inside the data frame, in almost every case, the internals are different and not compatible. And this creates a lot of problems. So in the context of a database system, suppose that you want to extend a database system with some custom code that is written in Python or written in R. So because the in-memory format of the database, the way it represents data in its runtime is not public, so there's no public API for the internal data. What they do is they define an intermediate API for writing extensions, and then serialize from their internal representation to that intermediate representation and expose that to you as a public API. That API is often row-based, and so if you're a Python programmer, you don't want to be running one Python function call for every row in a billion row data set. That's going to be, ridiculously slow. So, I arrived in the big data world at the end of 2014 after having a startup. I was at Cloudera. I looked around, so we've got to make Python and R first-class citizens in the big data world. How do we do that? And my feeling after assessing the ecosystem was, well, we have to solve this problem so that we can make data available to the data science world without having to go through a very narrow kind of serialization pipe. So there's a number of reasons why I think that things are so fragmented, and there has not been a prior effort to create standardization. So one thing is just open source communities are fragmented by their nature. Like, it's sort of an anarchy. There's no central government making decisions. It's very infrequent that you see developers from different communities come together. So I've started spending more time with the R community. The R community historically has not spent much time talking to other communities, the same with Python and others. So you can't really blame communities for focusing on their own needs and developing solutions for the problems that are right in front of them. I also think that some of the fragmentation is caused because people want to make the front end, the user API for these projects, they want to make it work exactly like in a particular way. So even within R, there's the tidyverse, and there's data.table, and there's base R. And part of the reason why there's so many different data frame APIs in R is because the user experience of using those libraries is completely different, even though the underlying data is just an R data frame. And in Python, the Pandas API is also a lot different from the R data frame API. But there's a lot of details of the way that Pandas is implemented that are visible in the public API. So if we wanted to make major changes to the internals, that would cause API breaks that would upset users. And we've just made the decision to try not to upset users very much, although I don't know that we've succeeded at all times. So kind of in response to this, I spent a lot of 2015 going around the open source big data world. It was a bit Bay Area centric because that's where I was physically at the time, and where I could meet with people in person and see if they were interested in working on this effort. And we were able to assemble a collection of about 25 people who are leaders in different open source data science and big data projects to commit to working together to creating an open standard for in-memory data frames that's column-oriented and suitable for analytic computing. And for me, what's really exciting about this, and I'm going to tell you more about in the next 20 minutes or so, is that I wanted to create the environment that would enable collaboration between the data science world and the database systems world, where historically they've been completely separate, and there's a lot of really great technology that's in the database world, but very little of that technology has made its way into data science. The only way that data scientists get access to that is by sending SQL queries into a database, and so I would like to see that change. So, kind of to recap our goal, the goal is to go from having non-portable data formats to portable data formats. So that's That's kind of the Arrow format, which I'm going to tell you more about. And my objective is to create libraries, high-quality libraries that handle the kinds of problems that you solve with pandas and with equivalent libraries in other languages that are reusable and can be ported and built, and you can use via binding layers in many different programming languages. So if you think about this in the context of analytic databases, so traditionally a database system or a data science library is vertically integrated. So your front end is usually SQL queries, and when the SQL query is parsed, the database creates a logical query plan. It looks at statistics and metadata about how the data is stored and what we know about the data. It creates a physical query plan. That query plan is executed by a computation engine, which might be single node, it might be distributed. That computation executes against data that's in memory, which may be deserialized from disk on the fly, or it may be cached in memory. And so that's where the in-memory format comes in. And then we have I/O subsystems for interacting with file systems, for reading and writing file formats. But usually all of this is not visible to external users. So you only see the front end, and the internals are deliberately made kind of part of the black box. And so if you wanted to extract code and reuse it, it would be very, very difficult. So our goal is to kind of deconstruct the analytic database to break things into libraries that have public APIs that are reusable, and you can pick and choose the components that you want to use to build a data processing system. So if you just want a fast data access and deserialization layer, you can use that. If you want, a way to share memory between processes, like deal with large data sets on disk, you can just use that. If you just want to use the library of algorithms and the memory format, it's sort of up to you. But the big picture is that we don't want to be prescribing the API and the front end, the way that you interact with the data. So if you want it to be SQL, you can make it SQL. If you want it to be Pandas-like or R-like, you can create an API that works like data frames in those languages. So, deconstructed database is deconstructed soup. That's sort of our goal. So the project, the use cases that we're concerned with are, or at least that I'm concerned with, are these three areas. So the first is being able to have very fast access to data, so being able to read and write data in all of the ways that it is stored. So that's dealing with storage formats like columnar Parquet files. It's being able to read and write data as efficiently as possible to database systems, because we can't just take all the data out of wherever it's stored and say, okay, we've got a new data format. It's not even a storage format, it's an in-memory format, so we can't move the data, but we need to get access to the data as quickly as possible from wherever it's stored. If you have data that is in Arrow format, we want to be able to move around data sets between processes and nodes as efficiently as possible. So the two areas that we're focused on there are shared memory and RPC, so socket-based communication. And then it would be kind of useless if you couldn't actually do anything with the data as is, if you just needed to convert it to some other representation all the time. So we're also developing computational libraries that evaluate natively against the Arrow format. So let me see, I need to move. I added some slides and then forgive me. So the Arrow format itself is an in-memory table-like format for representing data frames or representing a fragment of a table, like a chunk of a table inside a SQL engine. It's arranged, the way that the data is arranged in memory is optimized for analytical processing, so you wouldn't want to use it to build a mutable row store necessarily, but if you were building a columnar analytic database engine, that's what it's designed for. You can represent both flat and nested data, and it works well on both CPUs and GPUs, and we have people actively using the format on both types of types of hardware. So when you perform analytic operations, you only, because it's columnar, you only access the data that is relevant for your algorithms, and the access patterns to scan columns are efficient for the processor. So we've had a couple of things built in the last couple of years to help demonstrate kind of the benefits of using having more efficient data interchange and data transport. So in Spark 2.3, Spark 2.3 ships with optional Arrow support, which you can use in PySpark. And the idea is that, and I'll go back to the results here, is that Spark SQL has its own internal representation of tabular data inside Spark SQL, Spark data frames, depending on what part of Spark you're using. They could either be Spark data frames or just general Spark SQL. But Spark SQL does, its data is not resident in shared memory, so you can't do true zero copy sharing between processes. So if you wanted to make a large data set available to a Python process, maybe this is changing, but at least as far as, with my up-to-date knowledge, I don't think it's possible. But the way that it works is that Spark SQL serializes data to the Arrow columnar format that is streamed to the PySpark worker process. It's converted again to pandas, but then we built a layer to evaluate native pandas code against data, like chunks of data that are coming from Spark. And then this is streamed back to Spark via the Arrow format. And you might say to yourself, well, this is crazy, like we have 4 serialization steps, like we have to convert from Spark's internal format to Arrow format, then to pandas, then run some pandas code, then convert back to Arrow, to Arrow, and then from Arrow. So we have 4 serialization steps, so that can't possibly be efficient. But you have to remember, where did we start? And so there was already a multi-step serialization process that was happening, but that serialization format was particular to the Spark, PySpark bridge. And even with all of this serialization going on, the efficiency, with the efficiency of the Arrow format, these are some sample user-defined functions that are pandas-based. In some cases, we're able to get more than a 100x speed up in evaluating custom Python code. So if you see here on the left, suppose that you wanted to run, compute the cumulative probability function for a normal distribution inside Spark SQL. You can write that using SciPy stats. And when you're using Python, all of these functions that you have for analytics are they're intended to be invoked on NumPy arrays, and so you can use them on pandas objects as well. But if you were to, so the ideal mode is to invoke these functions on 1,000 values at a time, or 1,000,000 or 1,000,000,000 values at a time, not to run them once for every row in a data set. So even though we have all of this serialization work to do to move the data to and from Python, the efficiency gains are coming largely from changing the execution model from row-based to vector-based, and so batching the user-defined function evaluations. So that's cool. Another thing we're developing actively right now, in case this is relevant to you, is an RPC framework for building data services. So if you have a system and you want that system to be able to send around large data sets, this is a framework for defining custom data services. We're using GRPC, which is kind of become the gold standard open source RPC framework created by Google. The protocol uses protocol buffers, and so if you know about protocol buffers, you might say, well, protocol buffers, you have to parse them, and so how do we avoid that? Well, we spent some time doing some low-level optimizations in GRPC so that we can receive chunks of data from the server and interpret them as being Arrow data sets without having to do any additional parsing. So let's see here. So I kind of want to make this whole thing real to explain kind of how this zero copy thing works. So I'm just gonna, since I don't have a lot of time, I'm just gonna skip to the punchline, but all right. All right, so here on my local disk, I have an 11 gigabyte file. I hope this, I actually haven't tried this demo today, so maybe it doesn't work because, you know, open source, but so 11 gigabyte file, it contains a stream of table chunks that I wrote in one stream to disk. So we have like the notion of streaming data, so which has to be written from start to end. We also have a way to store data on disk that you can do random access and read a block from the middle of the table. And so what we can do in Python is memory map that file, open the stream, and then read all of the stream as a table. And so reading that entire 11 gigabyte file only takes about 10 milliseconds. And now we have a table in memory that has, let's see, 400 million rows, and I can access a column and then access any row in the data set. So if I want the 1,000th row or the 10 millionth row, they happen to all be the same in this case, but so I can do random access on this giant data set. And so in the context of, you know, streaming RPC, where a table is sending you batches of data, so what you can do is when you receive a chunk of data from the server, you can do whatever you want with it. You can buffer it in memory, you can stream it to a file. So suppose that a server sends you an unknown amount of data and possibly more data than you have RAM available. You can put all that data on disk and then memory map it and then proceed with your analysis. So compared with the way that like Pandas handles data, this is like a totally new world. So if you had implemented the RPC framework is called Flight. And so if you had built a server implementation, there's many different architectures you could do. You could have a planner node, which, you know, tells you like which servers to get the whole data set from. It might be distributed across many servers. The planner and the server with the actual data might be the same server. So there's many different ways you could set it up, but you request info about a data set, which is called a flight, and then you perform a series of gets to the underlying nodes that contain the data. And so those could be serial or parallel. And so just in the last month or so, we've created an implementation of this. And in C++ and so in Python, I'm able to move around about 3 gigabytes per second with a single thread on localhost. And that includes kind of end-to-end push data through the socket, receive on the other side, and have it ready to go, kind of memory mapped in memory. So it's a lot of cool stuff are possible with this. So if we have any data protocol nerds in the audience, so the way that things work under the hood is when you make a request to the server, a dataset GET request, it uses a GRPC stream to send a sequence of row batches back to the client. And so each of those row batches might be 1,000 rows or 1,000,000 rows, you know, depending on how you set things up. And even though the data is transported in a protocol buffer with some additional metadata, we were able to write a custom deserializer for gRPC both in Java and in C++ to be able to receive that payload and avoid doing any extra copying of the memory inside the protocol buffer so that we can interpret it as an arrow data set. So kind of our goal in building this technology is to create something that is high quality, very general purpose, and that you can take and put and use it as a library inside existing systems. So when you're doing RPC, so we've sort of said, you know, we don't care about what kinds of commands you execute. You can define custom commands for your clients and servers. So you could create a custom command that executes a SQL query. So this is a protocol buffer definition that contains a URI for a database and a query. You can send that in a get info RPC with type command, and then the server, if it understands that command, will send you back instructions how to retrieve the results of that query. But the kinds of commands you could send, it's up to you. You can implement whatever you like. So that's some stuff that's going on in the project, just in recent times. But we've been in development for almost 3 years now. We have almost 200 unique contributors. One of the areas that, in terms of building a large community of users, is that we've been trying to support as many programming languages as possible. We're now up to 10 programming languages. Not all of them have a fully complete set of functionality. So some of them are native implementations. So we have a native implementation in C++, Java, JavaScript, also in Rust and Go. And the rest are bindings. And so in Python, we interact with the C++ libraries directly. There's folks in Japan in the Ruby community who are working on Ruby bindings to this tech, and they're going through a C binding layer. But yeah, so we're kind of essentially adding as many programming languages as we can, and making sure that we're enabling people to access the data and access the libraries to be able to use those inside their systems. Another project that's going on that's pretty interesting is a expression compiler for creating higher performance analytic functions that evaluate against tables and data frames. So this came out of the Dremio Corporation, which they're building an open source project called Dremio, which is a kind of federated data access layer. It's SQL based, it's written in Java, and they wanted to accelerate the evaluation of the expressions that are found in the select part of a SQL query and the where part, so essentially projections and filters. And even though their system is written in Java, they created a compiler for these expressions that uses LLVM, so it's invoked from C++. And because there's a common memory format in Java and C++, that data can be exposed to the Gandiva compiler runtime through JNI without actually copying the memory, because it's just memory addresses that are coming out of off-heap JVM memory. So it's kind of always been the dream, and my dream, to be able to have zero-copy data sharing of complex data sets between the JVM and the native code world. And I guess it's only taken me 10 years to get here, but I'm glad that we're finally getting there. Some more use cases, but there's another exciting thing that's going on. So last year, NVIDIA got together a group of companies that are building and doing analytics on the GPU, either building databases that run on that do interactive analytics on the GPU. Companies like you might have heard of, like MapD. There's another company called Graphistry doing kind of in-browser graph exploration and visualization that's GPU powered. And the idea was to create libraries of reusable analytic functions for CUDA to enable, first of all, to enable data to be shared between one GPU-based system and another, and have a standard library of algorithms for doing feature engineering and data frame operations on data on the GPU. So they've called this the GPU data frame. It's essentially Arrow on the GPU. And the kinds of things that are possible now is that you can run a SQL query in MapD, which is a GPU-based database. You can ask MapD to leave that data, the results of the query, on the GPU. That data can be made available to another process using CUDA's built-in inter-process communication, so CUDA IPC. You can get a handle to that data in Python, and then write custom code in Python, compile it with Numba, which is using LLVM, and then run that directly on the data set in the GPU. And this is the kind of thing that if you didn't have a common data representation, this just would not be possible. Not be possible at all. So very cool stuff happening here. As time has gone on, I guess the number of companies and folks who are contributing or using Arrow has expanded. There's some folks, so one of the components of the project is a system for managing shared memory regions that's used in the Ray machine learning project, which is out of the RISE lab at UC Berkeley. And so we've had folks from kind of Alipay at Ant Financial contributing to the project, which is really cool since I think the running joke is always somebody from California meet somebody from China and they're like, oh yeah, we have big data, and they say, well, we've got this is China, we've got probably 10 times as much data as you do. So I think getting contributions from from folks in China is really important for ensuring that these systems are scalable to to kind of that level of data sizes. Sorry, I don't want to overwhelm you with technical detail, but so anyway, so as you can tell, this is stuff that I'm very excited about. A lot of people. See how much time I have, like what, 5 minutes? Yeah, 5 or 10 minutes, yeah. I'll make some time for some questions, but a lot of people ask me, like, Wes, like how can I use the software? Like how is this relevant to me? And it really depends. So if you're a data scientist or a data engineer, so my objective over the next, I've been working on this project for about 3 years, and there's easily 3 or 4 more years of work that I want to do on it. But there's one area which is I would like to deliver a natively Arrow-based kind of next generation data frame library that is a companion project to Pandas that's designed for working with very large data sets, that has memory mapping built in as its like key feature. So you can treat data on disk as though it's in memory. So if you have hundreds of gigabytes of data on disk, you can perform meaningful analytics on your laptop without having to spin up a Spark cluster. Okay, that came back. Because I think it is sort of sad that at the level, Pandas wasn't really designed for working with massive data sets, and so to have 5 or 10 gigabytes of data and be unable to perform joins in memory and have to write a Hadoop job or write a Spark job, it makes me sad. And I think part of the problem is that data science systems aren't internally are not architected like databases, so they don't have query planners. If you join 2 data frames and then want to immediately filter and aggregate, there's no way for Pandas to be able to optimize and evaluate that efficiently. That's something that we could build. That's something that we could hypothetically build inside Pandas, but that would be something that that would be code that's not really reusable outside of the context of Pandas. So, but I'd like to build all of this in a way that is not Python specific, so the R community can take advantage of kind of improved computational internals for data frames. Folks in the Ruby world can use that as well. Anyone who wants to build bindings to those libraries can take advantage of them. I think with the work on like faster RPC and messaging, I think we will see a wave of a lot of systems deprecating their existing data access and RPC layers in favor of natively Arrow-based messaging. So, to be able to move multiple gigabytes per second through a socket, and that's kind of end-to-end, traditionally messaging layers you might get a few hundred megabytes per second. So to have a 10x, 5 to 10x improvement in throughput improves, resource utilization. It removes a lot of the serialization time that's spent in distributed systems, so it's a clear win in terms of cost savings inside data centers. And I honestly envision a world that is built around the notion of data microservices, where you have a centralized metadata registry. You can see like, here's all of my data services available. I use the exact same client interface to access all of them, and you can push and pull data sets at high speed in a cloud or kind of cluster environment. But right now it's difficult because you use different clients to access data. You have to think about how's the data stored. Is it a Parquet file? Is it Avro? Is it, is it CSV? Like what library do I use? Like what settings do I use with that library? Like how do I parse the dates? Does this have missing data? How is this missing data represented in memory? So there's like, as a data scientist, data scientists are overwhelmed. Personally, I'm overwhelmed with like all of the complexity and things that people have to worry about just to deal with like, I want to read a data set, I want to perform some simple analytics and feature engineering and then use TensorFlow. And there's so much, stuff you have to deal with to get to the point of actually doing, like the actual science. So I would like to simplify that as much as possible and just make it about, I request a data set, I get the data set as fast as possible. I don't have to worry so much about all of these details, and I can get on with my work as a data engineer or data scientist. So hopefully that sounds good. But I think to build technology like this that kind of makes things less fragmented and helps unblock these use cases is a great deal of work. So people often ask me like, how long am I going to have to wait? But I think the next few years are going to be pretty impactful in terms of getting the software deployed in many places in production and beginning to make things faster and simpler. So thanks for listening. I guess maybe I have 5 minutes for questions.
Could you talk about schema evolution in the format, please?
Yeah. So the format is so first of all, it's not for long-term storage. So it's for ephemeral. Ephemeral storage and kind of for data transport. But I guess the question might be: suppose I have an old server sending data to a new client. So in the case that you have,
the case I was talking about is you had that disk on that file on disk, that Arrow file. Let's say you have a different schema with several different files.
Yeah. Oh, that's a temporary file, so that you wouldn't want to store that on HDFS and then come back and read it 7 years later. So in the event that your schema changes, you can look at the two schemas and project one to the other. We haven't written the projection code. So like hypothetically, you could say, here's the schema I want now, and read this file, but conform. If there's a new column that isn't on disk, then that column would have show up as all nulls in the result. But yeah, the schema is stored with the data, so you can look at the schema and decide what you want to do.
Hi, thanks for talking to us today. I was just wondering about you mentioned 2 Sigma as your early collaborator or some sort of like contributor. Can you elaborate on that a little bit and maybe talk about specific use cases or applications of Arrow in the hedge fund industry in general? Thank you.
Yeah. I guess I can't speak specifically to what 2 Sigma is doing with their data, but 2 Sigma has a petascale data warehouse and invests a lot of time and money in data collection. Has acquired companies that specialize in data collection, and I think that they view one of their most valuable sources of intellectual property as their data itself. Heavy Spark user, a heavy enough Spark user that they actively contribute to Spark. And have done significant internal developments to make Spark easier to use in a kind of multi-tenant setting in kind of large cloud and on-prem clusters. But they're also a heavy Python user, and so the reason that I went to work there is essentially the promise of making Python on Spark a lot better, which we did successfully do. And so, so my colleague Lee Jen at 2 Sigma did that work in collaboration with IBM, and they're also a big Java shop, and so the kind of improved interoperability between the Java JVM ecosystem and the native code world is very interesting for companies like 2 Sigma that have large, large Java-based systems.